A silent rain of cosmic rays connects your body to the most violent events in the universe. These are not rays of light, but high-energy particles born from dying stars, and they reveal a hidden web that links every corner of existence. By the end of this, you will understand how these messengers fundamentally connect you to every star and galaxy. We will trace their epic journeys from supernova explosions to our own atmosphere, exploring how they might even influence life's evolution. What invisible threads tie our world to the deepest reaches of space? To grasp their true nature, we must first let go of what the name suggests. Cosmic rays are not beams of light you could see. They are a ceaseless, invisible downpour of matter. Think of them as the universe's own subatomic bullets, almost entirely protons and the nuclei of atoms, accelerated across the galaxy to velocities that brush against the ultimate speed limit. The energy packed into a single one of these particles can be millions of times greater than what our most powerful machines on Earth can create. This is not gentle starlight. It is the raw, high-speed substance of stars themselves, flung across the void. Their journey begins in the most extreme environments imaginable, places where the very fabric of space and time is stretched to its limits. You stand in the sunlight, feeling its familiar warmth, yet you are a living gateway for an invisible storm. Trillions of these cosmic bullets pass through your hands, your head, your heart, every single second without a trace. This is not a distant abstraction. It is a direct physical tether. The same particles threading through you at this very moment have traveled for millions of years, carrying the signature of their violent origins. They are a whisper from a dying star, a breath from a galactic core, felt not with your senses but written into the very fabric of your being. This constant, unseen interaction is the universe's most intimate handshake, a humbling reminder that the boundary between our world and the cosmos is far more porous than it appears. To understand this connection, we must follow these messengers backward, retracing their epic journeys to the chaotic events that gave them life. Their story begins in the final, furious moments of a star much larger than our Sun. When such a star exhausts its fuel, its own immense gravity causes it to collapse in on itself in a cataclysmic rebound. This is a supernova, an explosion so brilliant it can outshine an entire galaxy. In that fleeting, unimaginable flash of energy, the outer layers of the star are blasted into the void, and protons, the building blocks of atomic nuclei, are caught in the blast wave. They surf this expanding sphere of fury, gaining incomprehensible speed until they become the very cosmic rays that will one day sweep through our solar system. But the supernova is only the beginning of the story. That initial, explosive push is just the first chapter in a far longer and more complex journey. The shockwave from the dying star does not merely eject these particles, it traps them within its own turbulent, expanding shell of gas and magnetic fields. For thousands of years, these atomic nuclei are caught in a chaotic, natural accelerator. They ricochet back and forth across the shockwave, gaining a little more speed with each crossing, like a ball being bounced between two rapidly approaching walls. This relentless process, called diffusive shock acceleration, is what hones the raw stellar material into the high-energy cosmic rays that eventually escape into the galaxy. Each particle becomes a fossil, preserving the violent physics of its birth. Yet even these titanic stellar explosions have their limits. They cannot account for the most extreme cosmic rays, the ones with energies so fantastically high that they defy belief. These ultra-high-energy particles carry as much kinetic energy as a professionally thrown baseball, all compressed into a single subatomic speck. Their existence points to sources of power far beyond a supernova, to engines of destruction that dwarf even the death of stars. To find them, we must look beyond the frontiers of our own Milky Way, into the vast dark gulfs between galaxies. These ultra-high-energy cosmic rays point to engines of cosmic destruction on an entirely different scale. To find their source, we must look to the hearts of distant galaxies, where supermassive black holes containing the mass of millions or even billions of suns are actively feeding. This is an active galactic nucleus, a cauldron of such ferocious power that it can outshine every star in its home galaxy combined. As vast clouds of gas and dust spiral inward toward the event horizon, a portion of this material is funneled into jets of plasma and radiation that blast outward at nearly the speed of light, stretching for thousands of light years into the void. It is within these relativistic jets, in their intense magnetic whirlpools, that protons and atomic nuclei can be accelerated to energies that make a supernova look tame. A single particle catapulted from one of these jets carries more energy than a major league fastball, all compressed into a speck smaller than an atom. Another candidate for these extreme accelerators is the gamma-ray burst, a fleeting flash of light that represents one of the most powerful explosions since the Big Bang itself. In a matter of seconds, a gamma-ray burst can release more energy than our Sun will emit across its entire 10 billion-year lifetime. The physics behind these events is still being unraveled, but they are thought to be the birth cries of black holes during catastrophic stellar collapses or the mergers of ultra-dense neutron stars. The resulting fireball, expanding at a breathtaking fraction of light speed, creates shock waves that could easily accelerate particles to these phenomenal energies. What these sources share is an almost incomprehensible capacity for violence, acting as natural particle cannons that fire their ammunition clear across the cosmos. This means a single particle arriving at our atmosphere could be a literal messenger from another island universe, a tiny piece of a galaxy so far away its light is just a faint smudge in our most powerful telescopes. Its journey began billions of years ago in a completely different corner of space and time. It has flown through the near-perfect vacuum between galaxies for eons, a solitary traveler on an epic voyage, until its path finally intersected with our tiny world. This establishes a direct material connection between separate island universes. You are not just linked to the stars of our own Milky Way. You are physically interwoven with the substance of galaxies far beyond our own. But this raises a profound puzzle. How does a single charged particle survive a journey of billions of years across intergalactic space? The universe is not entirely empty. It is filled with a faint sea of light, the leftover glow from the Big Bang, and tangled with the magnetic fields of galaxies. One might expect a proton traveling for so long to slowly lose its energy, colliding with this background radiation or being deflected endlessly by magnetic fields until it becomes lost. The very fact that these ultra-high-energy particles reach us at all is a clue that their journeys are not simple straight lines, and that the empty spaces between galaxies are far more structured and interesting than they appear. Their survival is a testament to their incredible initial speed and a hint that the cosmic web itself may be guiding them. This magnetic guidance transforms the void into a structured labyrinth. A cosmic ray does not fly a straight path from its source to your outstretched hand. Instead, it is a spiraling prisoner caught in the grip of the galaxy's invisible magnetic fields. These fields are unimaginably faint, far weaker than a common refrigerator magnet, yet they stretch across light years, weaving a complex web. They act as the ultimate cosmic highway system, complete with winding on-ramps, curved overpasses, and endless detours. A particle born in a distant supernova may spend millions of years tracing this intricate network, corkscrewing its way through the void, its origin utterly scrambled by the journey. This deflection is not a flaw in the system. It is its most vital feature. Without this magnetic cushioning, the highest energy particles would slam into the faint background radiation that fills all of space, losing their immense energy in a flash of light long before they could reach us. The magnetic fields gently curve their paths, steering them around the most direct and dangerous routes, allowing them to survive their epic trans-galactic voyages. This is the infrastructure of connection, the reason a whisper from a galaxy far, far away can still find its way to our doorstep. Our own solar system is not a passive destination in this network. It is an active participant, a local hub with its own magnetic defenses. The Sun constantly exhales a stream of charged particles known as the solar wind, which carries the Sun's magnetic field outwards to form a vast protective bubble called the Heliosphere. This bubble envelops all the planets, acting as a shield that deflects and modulates the incoming torrent of lower-energy galactic cosmic rays. When the Sun is most active, with frequent solar storms and a stronger wind, the heliosphere swells, pushing back against the cosmic rays and reducing their numbers within our solar neighborhood. During the Sun's quiet periods, the shield weakens slightly, and more of these ancient particles pour in. This means the cosmic ray flux at Earth is in a constant, gentle dance with the rhythm of our own star's 11-year cycle. You are connected not only to the distant cataclysms of deep space, but also to the immediate, breathing activity of our Sun. This protective bubble is our first line of defense, a dynamic filter that breathes with the rhythm of our star. But what happens when the cosmic rays that slip through this shield finally meet a world like our own? Their journey is far from over. They are about to collide with the thin, precious veil of our atmosphere, triggering a cascade of creation and destruction that rains down upon the surface. This is where the invisible becomes, for a fleeting moment, visible. When a high-energy proton from a distant galaxy slams into a molecule of air high above your head, it does not simply bounce off or pass through. It unleashes a spectacular subatomic firework display. The impact shatters the nucleus of that air atom, blasting it into a spray of secondary particles, pions, muons, electrons, and more. These newborn particles, themselves carrying immense energy, then collide with other nuclei, creating an ever-widening shower of matter. What began as a single cosmic bullet transforms into a vast, invisible umbrella of particles, spreading out for miles as it plummets toward the ground. This is an air shower, a silent, relativistic avalanche born from a single whisper of the cosmos. You are standing directly beneath these cascades right now. The particles that eventually reach you, the ones gently threading through your body every second, are the surviving descendants of those initial, violent collisions high in the sky. They are the cosmic echo, the final, faint whisper of a chain reaction that began with a star's death billions of years ago. This atmospheric interaction does more than just deliver these messengers to our doorstep. It fundamentally alters them, transforming their original, pristine state into a complex rain of secondary particles. The primary cosmic ray, which carried the unique signature of its source, is gone, its identity lost in a storm of its own making. We are left to study its children and grandchildren, piecing together the story of their origin from the fragments that survived the journey to the surface. This presents a fascinating challenge for scientists. How do you trace a ghost back to its homeland when it changes its form just before arrival? The answer lies in decoding the subtle clues left in the shower itself, the specific mix of particles, their energies, and the angles at which they arrive. Each air shower is a unique fingerprint, a chaotic but information-rich signature that can tell us about the mass, energy, and even the possible direction of the primary particle that started it all. This is how we listen to the universe, not by catching the original message, but by carefully studying the ripples it creates in our own air. This constant, invisible rain does more than just pass through our air. It actively reshapes it. When a high-energy cosmic ray strikes the top of our atmosphere, that collision is a direct transfer of raw power from the depths of space into our planetary environment. The resulting air shower is not merely a spectacle, it is a chemical engine. The cascade of secondary particles, particularly electrons, can break apart the stable molecules of our air, creating a trail of ionized atoms and highly reactive fragments. These fragments then trigger chains of chemical reactions they would not normally undergo, subtly influencing the composition of the very air we breathe. On a world like Earth, this process can contribute to the formation of cloud condensation nuclei, the tiny seeds around which water vapor coalesces to form clouds. This suggests a remarkable possibility that the grand climate systems of our planet may be gently nudged by the echoes of dying stars from millions of years ago. Our atmosphere is not a static shield. It is a dynamic, living canvas upon which the cosmos paints with invisible, high-energy brushes. This interaction also contributes to the natural background radiation that is part of our world. The surviving particles from these air showers, especially muons, reach the ground and pass through us, adding a minuscule but measurable dose to the radiation we experience throughout our lives. It is a humbling reminder that we are not separate from the universe's processes. We live within them, and our bodies have evolved in the presence of this gentle, cosmic background. This leads to a profound question that reaches beyond physics and chemistry. If cosmic rays can influence atmospheric chemistry and deliver a steady, low-level radiation dose across geological time, could they have also played a role in the story of life itself? The subtle mutations they cause in delicate DNA could act as a slow cosmic timer, perhaps even influencing the pace and direction of evolution on our world. This biological link turns the vast cosmos into a quiet participant in life's grand story. The same particles that spark ethereal northern lights also interact with the delicate double helix of DNA within every living cell. When a high-energy cosmic ray, or more often one of its secondary particles, passes through organic tissue, it can slice through DNA strands like an impossibly tiny blade. This damage is an ionization event where the particle's energy knocks electrons loose from atoms in the molecule, breaking its structure. Your body is a master of repair, constantly fixing these microscopic cuts with elegant biochemical machinery. Most of the time, the damage is mended perfectly, leaving no trace, but occasionally a repair is not quite perfect. A tiny genetic mutation is introduced, a single letter changed in life's immense instruction manual. The overwhelming majority of these changes are neutral, having no effect at all, and a very small number can be harmful. Yet, once in a great while, a mutation might offer a subtle advantage, a new trait that helps an organism survive or reproduce just a little better in its environment. This is the raw material of evolution, and cosmic rays provide a steady background source of it. The rate of these random genetic changes is not set solely by Earth's internal chemistry. It is gently paced by the cosmic weather, by the ebb and flow of high-energy particles born from stellar explosions and active galactic nuclei. Life on Earth has evolved under this soft rain for billions of years. The very diversity of species around us, including our own existence, is therefore woven from threads that lead back to the deaths of distant suns. This connection transforms our understanding of life from a purely planetary phenomenon to a truly cosmic one. Any world with a thin atmosphere and a magnetic field weaker than our own would experience a much heavier downpour of this mutagenic rain, potentially accelerating the pace of evolutionary change. The story of life anywhere in the universe may be fundamentally shaped by the stellar activity in its home galaxy. To truly grasp this connection, however, we need to move from the theoretical to the tangible. We must catch these particles in the act. How do you build a trap for a ghost, an object that moves at nearly the speed of light and passes effortlessly through solid rock? The quest to answer this question has driven scientists to create some of the most ingenious and vast experiments on the planet. To capture a ghost, you must build a net on a scale that seems almost impossible. These particles arrive one at a time, yet their footprints are vast, spanning dozens of square kilometers in an instant. The solution was to turn the entire sky into a laboratory. At the Pierre Auger Observatory in Argentina, an array of 1,600 water tanks is scattered across a plain as large as a small country. Each tank sits waiting, a silent sentinel in the darkness. When the invisible cascade of an air shower rains down, the particles strike the pure water within these tanks, traveling faster than light can move through that medium. This creates a faint, ethereal blue glow known as Cherenkov radiation. The entire array acts like a colossal camera, with each tank recording a single pixel of the immense shower. By timing the arrival of the light across these widely separated detectors to within a billionth of a second, scientists can reconstruct the precise trajectory and staggering energy of the primary cosmic ray that started it all millions of years ago and billions of light years away. The data does not arrive as a simple return address. It is a complex puzzle of probabilities. When researchers at Auger and other giant observatories like the Telescope Array in the United States began mapping the arrival directions of the most energetic cosmic rays, they did not see a perfectly uniform scatter. They noticed faint, clustering patterns in the celestial map, subtle statistical overdensities that point back toward specific regions of the sky beyond our Milky Way. These are not pinpoints of light, but rather broad smudges on the cosmic canvas, hinting at sources in the distant, lumpy web of galaxies. This is how we listen to the universe. We are not catching the original particle. We are studying the echo of its final, explosive interaction with our world, using that echo to trace a path back through the dark. These observatories are more than just scientific instruments. They are our planet's listening posts, giant ears cupped toward the heavens, patiently decoding a story written in high-energy ink. The messages they collect are slowly revealing the architecture of the cosmic accelerators themselves, telling us not just where these particles come from, but how the most violent engines in the universe actually work. This cosmic map is not a uniform blur. If the rain of cosmic rays were perfectly even, the sky would look the same in every direction, a featureless static of high-energy particles. But it does not. When scientists created detailed charts of their arrival, they discovered a subtle imbalance, a gentle lopsidedness in the heavens. One broad region of the sky appears slightly warmer, a diffuse hotspot where just a few more particles arrive. In another direction, there is a corresponding cold spot, a quiet patch in the invisible storm. This slight unevenness is called anisotropy, and it is a profound clue written into the fabric of the cosmic rain. It tells us that the flood is not coming from infinitely far away. If it were, the journey through the tangled galactic magnetic fields would have scrambled all direction completely, leaving no trace of a source. The fact that we can see any pattern at all means that a significant portion of the particles washing over us must originate relatively close by, within our own galactic neighborhood. We are not just hearing the distant roar of the entire universe. We are picking up the distinct voices of nearby cosmic loudspeakers. Deciphering this pattern is the ultimate exercise in celestial cartography. That hotspot is not a single bright point like a star. It is a vast, faint smudge on the sky, a statistical preference pointing toward a specific spiral arm of our Milky Way, a region rich with stellar nurseries and the expanding shells of ancient supernova remnants. These are the local accelerators, the stellar engines within our own galaxy that are currently active, broadcasting their presence across the light years. Every time a massive star explodes in our cosmic backyard, it injects a fresh wave of these particles into the local magnetic highway, creating a temporary surge, a ripple in the anisotropic map that we can slowly learn to read. This brings us to the final and most difficult step in the entire cosmic ray mystery. We have the map. We can see the general neighborhoods where the broadcast is strongest. But how do we pinpoint the exact address? How do we move from a blurry hotspot to a specific, named supernova remnant? The fundamental problem remains the same. Cosmic rays are not light. They are charged particles, and their paths are twisted into spirals by magnetic fields. By the time one reaches our detectors, its original direction of travel has been completely erased. It is like trying to find the source of a leaf that has just floated down a winding, turbulent river. You know it came from somewhere upstream, but the complex currents have hidden its precise point of origin. So we must become cosmic detectives, using indirect evidence to build our case. We look toward a hotspot with our most powerful telescopes, searching for the telltale glow of a supernova remnant's expanding shockwave. We then use sophisticated models to simulate how particles would travel from that specific location through our best maps of the galaxy's magnetic field. If the simulated arrival pattern at Earth matches the real anisotropy we observe, we have found a likely culprit. It is a painstaking process of matching a cosmic fingerprint, a slow and meticulous unraveling of the universe's most intricate threads. Pinpointing a single cosmic ray's origin is like finding one specific leaf in a planet-wide river system. The direction from which a particle strikes our atmosphere is a final, scrambled destination, not a starting point. Galactic magnetic fields act as a cosmic maze, twisting the path of every charged particle into a spiraling, unpredictable route that completely obscures its source. This is the fundamental challenge of cosmic ray astronomy. You are trying to read a letter that has been through a shredder and then scattered by the wind. To solve this, scientists have turned to a powerful new strategy called multi-messenger astronomy. Instead of relying on cosmic rays alone, they correlate their data with other, more direct cosmic messengers. Gamma rays, for instance, are pure light and travel in straight lines, pinpointing violent events with precision. Neutrinos, ghostly particles that barely interact with matter, can fly directly from an accelerator's heart without being deflected. Even gravitational waves, the ripples in spacetime itself, can signal a catastrophic merger. When a surge of high-energy cosmic rays is detected at the same time and from the same general region of sky as a flash of gamma rays or a pulse of gravitational waves, the separate clues begin to form a single, coherent story. This collaborative detective work across different fields is slowly building a case against specific cosmic suspects, from active galactic nuclei to colliding neutron stars. Yet even with this powerful approach, some particles defy all classification. Their energies are so impossibly high that they challenge our very understanding of physics. In 1991, a single event in the Utah desert redefined the upper limits of cosmic violence. A solitary cosmic ray struck the atmosphere with an energy that seemed to defy the laws of physics. A particle moving so fast that in the thin air high above the Earth, it was outpaced only by light itself in a perfect vacuum. The detectors registered an energy level that was staggering, equivalent to a baseball traveling at 60 miles per hour, all compressed into a subatomic speck. The scientists who discovered it had a simple, awestruck reaction, naming it the "Oh my God" particle. Its existence is more than a record, it is a direct challenge. What kind of natural event could possibly serve as a cannon for such a projectile? Our most powerful particle accelerators on Earth are like children's toys compared to this cosmic engine. To give a single proton this much energy requires a natural process of almost incomprehensible ferocity, something far beyond the shockwaves of supernova or even the relativistic jets of active galaxies. This particle is a message from a place where the known rules of physics are stretched to their absolute breaking point. It hints at cosmic catastrophes we have not yet even named, events that may have occurred when the universe was young and far more volatile. The very fact that it reached us is another piece of the puzzle. A particle with this much energy should not be able to travel great distances through space. It should collide with the faint background radiation left over from the Big Bang, losing its immense energy in a flash of light and never completing its journey. The "Oh my God" particle did arrive, which means its source cannot be infinitely far away. It must have been born within a relatively nearby volume of the cosmos, perhaps within our own local supercluster of galaxies. This places an incredible engine of destruction in our own cosmic backyard, a silent, invisible titan whose presence we only know from a single, ghostly impact. Finding it is the next great hunt in astronomy. These ultra-high-energy cosmic rays are the ultimate test of cosmic connectivity. They represent the most extreme handshake from the universe, a thread pulled so taut with energy that it threatens to snap our understanding of how everything is linked. Unraveling their origin is not just about cataloging another celestial phenomenon. It is about probing the absolute limits of power in the cosmos and discovering what fundamental processes are capable of weaving such a powerful thread into the fabric of our existence. The universe itself places a speed limit on these cosmic messengers. This is the GZK Cutoff, a theoretical wall born from the faintest echo of creation. The entire cosmos is filled with the cosmic microwave background, a cold bath of radiation that is the cooled remnant of the Big Bang's first light. For an ultra-high-energy proton traveling across intergalactic space, this background radiation is not a harmless glow. It is a thick fog. A proton moving with enough energy should constantly collide with these ancient photons, and each collision would rob it of a little more speed, sapping its strength over a cosmic distance of about 160 million light-years. According to our best theories, no particle should be able to reach us from further away than that with its extreme energy intact. It is a fundamental barrier written into the fabric of space-time itself. Yet we keep catching cosmic rays that have smashed right through this theoretical wall. The "Oh my God" particle was not an isolated event. Others have been recorded with energies that blatantly defy this cosmic speed limit. Their very existence forces us to confront two equally staggering possibilities. Either there are sources of unimaginable power lurking almost right next door to our Milky Way, cosmic accelerators of a ferocity we have never observed, quietly operating within our local galactic neighborhood. Or our understanding of how matter behaves at these ultimate energies is flawed, and the laws of physics as we know them need revision on the grandest scale. This is not a minor discrepancy in a textbook. It is a direct challenge to our map of reality. The GZK cutoff was supposed to define the ultimate horizon for the cosmic ray connection, the maximum distance across which a high-energy particle could maintain its identity. The fact that particles arrive from beyond this horizon means the threads that bind the cosmos are stronger, and perhaps stranger than we ever dreamed. Every one of these ultra-high energy events is a message from a place that, by all rights, should be silent. These ghostly particles are far more than silent messengers from the void. They are active sculptors, their combined force shaping the very architecture of galaxies. Picture the immense collective energy of trillions of cosmic rays, all trapped within the magnetic web of a galaxy like our own Milky Way. This creates a powerful, invisible pressure, a form of cosmic steam that pushes outward against the gravitational pull of all the stars and dark matter. This pressure is vital. It helps to support and amplify the galaxy's sprawling magnetic fields, preventing them from simply collapsing under their own weight. These magnetic fields are the very highways that guide the cosmic rays, and in turn, the particles provide the energy to sustain the roads they travel on. It is a beautiful, self-perpetuating cycle. This relationship becomes a driving force for the galaxy's own breath. The relentless pressure from cosmic rays can help power immense galactic winds, vast streams of superheated gas that flow from the heart of a galaxy out into the intergalactic void. This is not a gentle breeze, it is a hurricane of matter carrying away the raw material for future stars. That material is cosmic fuel, the hydrogen gas that would otherwise collapse to form new suns. By driving this gas out, the cosmic ray-powered wind effectively regulates the galaxy's star-forming factory. It places a cosmic governor on the birth rate of new stars, preventing a galaxy from burning through its fuel in a single, brilliant burst. This reveals a profound cosmic feedback loop. The violent death of massive stars in supernova creates the cosmic rays. Those same cosmic rays then help clear away the star-forming gas, directly influencing the rate at which new stars can be born. The death of one generation of stars therefore sculpts the conditions for the next. Over billions of years, this slow, steady pressure helps determine whether a galaxy becomes a dense, star-packed elliptical or a grand, star-forming spiral like our own. The invisible rain connecting your body to the stars is on a galactic scale, a fundamental force of creation and balance. The same high-energy particles threading through you might also carry whispers from the universe's greatest secret. For decades, we have known that the stars and galaxies we see are only a fraction of what is truly there. The cosmos is dominated by an invisible substance, dark matter, whose gravitational pull guides the motion of entire galaxies yet has never been directly seen. Its nature is one of the most profound mysteries in science. But what if cosmic rays are our first tangible connection to this hidden world? Some of the most compelling theories suggest that dark matter is not entirely silent. In regions where it is densely concentrated, such as the cores of galaxies, dark matter particles might occasionally collide with one another. When they do, they could annihilate in a flash of energy, transforming into particles we do know and can detect, including the familiar protons and their antimatter twins, antiprotons, that travel to us as cosmic rays. We are not just listening to the deaths of stars, we might be overhearing a conversation happening in the dark. The challenge is picking out that specific whisper from the cosmic roar. Scientists meticulously chart the precise energies of the cosmic rays raining down upon us, creating a detailed cosmic spectrum. If they find an unexpected, unexplained excess of particles at a very specific energy level, a spike that cannot be accounted for by any known stellar process or supernova remnant, it could be the long-sought smoking gun. It would be the unique fingerprint of a dark matter particle with a specific mass, annihilating in the void and sending a fragment of its being across the light years to our detectors. This transforms our understanding of the cosmic connection. You are linked not only to the brilliant, visible universe of stars and galaxies, but also to its vast, unseen architecture. The invisible rain is a bridge between the world we see and the mysterious, dark foundation upon which it is all built. Unlocking this code would mean that the same particles passing through your hand are messengers from both the light and the shadow, telling the complete story of the cosmos. These cosmic messengers are not all the same age. A single moment's rain contains particles from vastly different epochs, a mixture of ancient travelers and fresh arrivals. Some of these protons and atomic nuclei were forged and flung into the void just a few thousand years ago, born in supernova remnants that are, by cosmic standards, brand new. Others are the true veterans, having wandered the spiral arms of our galaxy for millions of years, their paths a tangled record of the magnetic maze they have traversed. This means that when we build a detector to catch them, we are not just building a scientific instrument. We are constructing a time machine, one that gathers a direct sample of the galaxy's evolving history. The key to reading this history is locked not just in their energy, but in their very substance, in the specific atomic isotopes that make up each particle. Every element tells a story of its birth. The common stuff of life, like carbon and oxygen, was cooked in the cores of stars. Heavier elements, like gold and uranium, require the even more extreme conditions of a supernova explosion or colliding neutron stars. When a cosmic ray is a nucleus of a heavier element, it is a literal piece of one of these stellar forges, a fragment hurled across space. But the story gets even more detailed when we look at the specific isotopes, the different versions of an element that have varying numbers of neutrons in their core. Some of these isotopes are stable, enduring forever. Others are radioactive, decaying away at a precise, known rate. By measuring the ratio of a radioactive isotope to its stable counterpart in the cosmic ray flux, scientists can perform a kind of cosmic carbon dating. If they find a high proportion of a fast-decaying isotope, it means those particles are fresh from their source, having had little time to decay during their journey. A lower proportion points to an ancient journey, one that has lasted for millions of years. This turns the invisible rain into a rich, layered archive. It allows researchers to distinguish the recent output of a nearby supernova from the background murmur of ancient stellar explosions, effectively separating the breaking news from the historical record. This isotopic clock also reveals the conditions inside the stellar furnaces themselves. The exact mix of elements and isotopes created in a supernova blast depends on the temperature, density, and available ingredients in that specific star. By carefully measuring the abundance of each type of nucleus in the cosmic rays we collect, we can work backwards. It is like analyzing the chemical signature of ash from a fire to determine how hot it burned and what was thrown into the flames. This data provides a direct test of our models of stellar nucleosynthesis, the cosmic process that builds the periodic table from hydrogen and helium. We are no longer just theorizing about how stars create the elements. We are holding the products in our hands, or more accurately, in our detectors. This continuous delivery of stellar material establishes a direct material link between the chemical evolution of our entire galaxy and the ground upon which we stand. The iron in your blood, the calcium in your bones, every atom in your body that is heavier than hydrogen was once created in a star and scattered across the galaxy, perhaps by the very same cosmic ray processes we are discussing. You are not just physically connected to the cosmos by particles passing through you. You are, in a very literal sense, made from the substance of stars, and cosmic rays are the ongoing delivery service for that galactic inheritance. Hidden within the cosmic rain is a ghost of a substance that should not exist. Among the countless protons and atomic nuclei, detectors have also captured their perfect opposites, particles of antimatter. A positron, for instance, is the mirror image of an electron, identical in every way except for its positive charge. When matter and antimatter meet, they annihilate each other in a pure flash of energy, vanishing from our universe. So why would we find these self-destructing phantoms traveling across the galaxy? The presence of antimatter is one of the deepest puzzles in the cosmic ray story. We know some of it is created in secondary processes. When a regular, high-energy proton from a supernova slams into a stray atom of interstellar gas, the colossal energy of that crash can spontaneously condense into new particle pairs, matter and antimatter blossoming from the void together. This should produce a certain predictable amount, yet when we count the antimatter arriving at Earth, the numbers do not quite add up. There is a persistent, puzzling excess of positrons, a surplus that whispers of something else at work. This anomaly is a clue pointing toward hidden cosmic engines. One compelling suspect is the pulsar, the rapidly spinning, magnetized core of a dead star. These celestial lighthouses beam out intense radiation and whip particles to fantastic speeds, creating swirling clouds of energetic matter around them. Within these turbulent environments, the conditions are perfect for spontaneously generating pairs of electrons and positrons, which could then escape into the galaxy as cosmic rays. Another, more profound possibility touches the nature of dark matter itself. If dark matter particles are their own antiparticles, then when two of them collide in the dense heart of our galaxy, they would annihilate, producing a spray of particles that includes this very excess of positrons we detect. The antimatter enigma transforms these cosmic rays from mere messengers into a unique diagnostic tool. They are sensitive probes for physics we cannot see with light. By meticulously measuring the exact energy spectrum of these antiparticles, scientists can look for a telltale signature, a specific spike or cut off in the energy that could only be produced by one type of source. It is like listening to the distant echo in a canyon and being able to determine not just that someone is there, but whether they are shouting, singing, or something else entirely. This search is a delicate one, sifting a faint, exotic signal from an overwhelming background of ordinary stellar noise. Each antimatter particle that reaches our detectors is a potential key, one that could unlock the identity of the universe's dominant yet invisible component, or reveal the intricate physics whirring inside a distant pulsar's furious heart. This invisible rain is a direct physical threat beyond our atmosphere. For an astronaut floating in the void or a satellite humming in orbit, cosmic rays are not a philosophical curiosity. They are a relentless bombardment that can scramble delicate electronics with a single, precise strike, causing phantom commands, memory errors, or even permanent system failure. This is the reality of space weather, a practical danger that ties the future of human exploration directly to the ebb and flow of galactic particles. The greatest risk, however, is to life itself. Beyond the protective cushion of Earth's magnetosphere, astronauts are exposed to a much heavier dose of this ionizing radiation. Each high-energy particle, or the secondary shrapnel it creates, can slice through living cells, damaging DNA and increasing the long-term risk of serious health challenges. A mission to Mars, for instance, would expose a crew to radiation levels equivalent to a whole-body CT scan every 5 or 6 days for the entire journey. This is the ultimate paradox of our cosmic connection. The same particles that subtly influence evolution on Earth become a genuine hazard for humans who leave its cradle. The source of this danger has two faces. The first is the galactic cosmic ray background, the ancient particles from distant supernova that the Sun's heliosphere struggles to hold back. During solar minimum, when our star is quiet, this shield weakens and the galactic radiation pouring into the inner solar system increases. the second, more immediate threat comes from our own star. Solar flares and coronal mass ejections can accelerate protons to tremendous energies, creating solar cosmic rays. These events can deliver a sudden, intense blast of radiation, a storm that requires astronauts to retreat to shielded quarters and can blind satellites temporarily. This means the safety of human spaceflight depends on our ability to forecast this cosmic climate, to predict when the sun will rage and when the galactic winds will pick up. We are learning to read the subtle signs, to see the connections between a sunspot on our star and the radiation dose an astronaut receives near the moon. Your body is a gateway for this cosmic stream, but for those who venture into the river itself, understanding its currents is a matter of survival. Our planet's own magnetic shield is the next critical layer in this cosmic defense. Generated by the churning of molten iron in Earth's core, this invisible force field extends thousands of kilometers into space, creating a protective bubble known as the magnetosphere. It acts as a sophisticated gatekeeper for the entire planet, bending the paths of incoming charged particles and funneling the vast majority of them harmlessly around our world toward the magnetic poles where they spark the auroras. This magnetic shield is our frontline defense, and its strength is the difference between a living world and a barren one. Compare the fates of Earth and Mars. Our world, with its robust dynamic magnetic field, maintains a thick atmosphere and enjoys a much lower surface radiation dose. Mars, however, lost its global magnetic field billions of years ago. Without that protective bubble, the solar wind stripped away much of its atmosphere, leaving the surface exposed to the full, unfiltered intensity of galactic cosmic rays and solar radiation. The radiation environment on the Martian surface is hundreds of times more intense than on Earth. This stark contrast reveals a profound truth in the search for life beyond our world. A strong magnetosphere does more than just deflect particles. It helps a planet cling to the very air and water that life requires. This directly links the violence of distant astrophysics to the fundamental question of astrobiology. The invisible architecture of a planet's magnetic field becomes a primary factor in its potential to nurture and sustain a biosphere. It is a cosmic prerequisite for a living world, a silent, magnetic heartbeat that holds the line against the storm. This subtle interplay between the cosmos and our climate begins high in the atmosphere, where a cosmic ray's journey ends in a burst of creation. When an energetic particle from a distant supernova strikes an air molecule, it does not just produce a shower of secondary particles. It also creates a trail of ionized atoms, electrically charged fragments that are exceptionally sticky. In the thin, cold air of the lower stratosphere and upper troposphere, these ions can act as anchors. They attract clusters of water vapor and trace gases like sulfuric acid, slowly building them into stable molecular assemblies. These tiny clusters are the embryonic seeds of clouds, known as aerosol particles or cloud condensation nuclei. Without these microscopic anchors, water vapor would struggle to condense into droplets, even in supersaturated air. The cosmic ray provides the initial spark, the charged platform upon which a cloud droplet can begin to form. This proposed mechanism, known as ion-mediated nucleation, suggests that the rate at which these cloud seeds form could be tied to the intensity of the cosmic ray rain. When the solar wind is weak and more galactic cosmic rays penetrate our system, the theory suggests we might see a slight increase in cloud formation. Conversely, when the sun is active and the cosmic ray flux drops, fewer seeds would form, potentially leading to less cloud cover. This creates a hypothetical but deeply profound link, where the death throes of a star hundreds of light years away could influence the amount of sunlight reflected back into space by our own planet's clouds. climatic implications of such a connection are immense. Low-level clouds in particular act like a planetary sunshade, cooling the Earth by reflecting solar radiation. If the cosmic ray flux truly influences global cloud cover by even a small percentage, it could nudge the planet's temperature over decades and centuries. This introduces a cosmic heartbeat into the Earth's climate system, a slow, rhythmic pulse driven by the 11-year solar cycle and the longer-term wanderings of our solar system through the galaxy's spiral arms. Researchers have delved into the historical record, examining ice cores and sediment layers for clues. They look for correlations between periods of low solar activity, which allow more cosmic rays to reach Earth, and evidence of cooler, cloudier climates in the past. Some studies have found intriguing hints of such a link, like the notable dip in solar activity during the Little Ice Age, a period from roughly the 14th to the 19th centuries when glaciers advanced and winters were famously harsh. The potential correlation is tantalizing, suggesting that the sun's influence on climate may extend beyond simple changes in brightness, working through this invisible, charged rain. Yet this idea remains one of the most contentious in modern geophysics. The chain of events from a single ion to a planet-spanning cloud deck is long and complex, with many other factors at play. The atmosphere is a chaotic system, and isolating the specific signal of cosmic rays from the overwhelming noise of ocean currents, industrial pollution, and volcanic aerosols has proven incredibly difficult. Many large-scale analyzers of cloud cover data have failed to find a strong, unambiguous signal. The scientific community is divided, with some researchers seeing a subtle but significant effect and others finding the evidence too weak to be conclusive. The debate itself is a testament to the complexity of our planet. It forces us to consider Earth not as an isolated sphere, but as a dynamic world immersed in a flowing river of galactic energy. Whether this cosmic connection is a major driver or a minor whisper, its investigation reminds us that our climate is a story written not just on Earth, but across the light years. The same particles that spark the northern lights may also be the hidden trigger for the sky's most dramatic spectacle. Deep within a brewing thundercloud where ice crystals collide and build up immense electrical charges, the final step to a lightning bolt has long been a mystery. What provides the initial spark that bridges the gap, creating a conductive path for that pent-up energy to violently discharge? The answer might be falling from the sky at nearly the speed of light. This is the runaway electron avalanche theory, and it places cosmic rays at the heart of the storm. When a high-energy particle from a distant supernova slams into the upper atmosphere, it creates a cascade of secondary particles, including a wave of free electrons. As this shower plummets toward the charged environment of a thundercloud, these electrons can be accelerated by the intense electric fields. They gain so much energy that when they collide with air molecules, they knock loose even more electrons, which in turn are accelerated and collide again. This creates a self-reenancing avalanche of charged particles, a sudden, conductive river of electricity that cuts through the air. This ionized pathway, born from a galactic particle, becomes the perfect wire, the initial leader that guides the colossal lightning strike to the ground. If this link holds, it means the brilliant fork of lightning that splits the sky is not merely a terrestrial weather event. It is the final, explosive step in a chain reaction that began with the death of a star millions of years ago. The flash that illuminates the storm clouds is, in its first instant, a spark from the galaxy itself. Even the dead stars continue to broadcast their power across the galaxy. When a massive star ends its life in a supernova, the core that remains does not always fade into darkness. If it is dense enough, it can collapse into a spinning sphere of pure neutrons, just a dozen miles across yet weighing more than our Sun. This is a pulsar, a stellar corpse that spins hundreds of times every second, sweeping the cosmos with lighthouse beams of radiation. Its power comes from a marriage of incredible extremes, a ferocious magnetic field trillions of times stronger than Earth's, combined with a rotation so rapid it defies intuition. This spinning magnetic field acts like a colossal, natural generator, creating electric potentials so vast they can literally tear electrons and their antimatter counterparts, positrons, right from the pulsar's surface. These particles are then caught in a whirlwind, accelerated along the star's twisting field lines to velocities that brush against the ultimate speed limit. The result is a pulsar wind nebula, a glowing cloud of high-energy particles that surrounds the spinning core like a cosmic engine's exhaust plume. The famous Crab Nebula is one such powerhouse, its heart a pulsar that beams energy into the cloud of its own making, illuminating the gas and continuously injecting a fresh stream of relativistic particles into the galactic void. This reveals a crucial nuance in the cosmic ray story. It is not only the violent death of a star in a supernova blast that creates these messengers. The long, active afterlife of that star's remnant is itself a prolific and enduring source. For thousands of years after the initial explosion, a pulsar can keep broadcasting, steadily contributing to the population of high-energy particles that wash through our galaxy. This means the cosmic network is not just fed by brief, catastrophic events. It is also sustained by these long-lived, rotating dynamos, these undead stars that refuse to go quietly into the night. They add a persistent hum to the cosmic background, a steady drizzle of high-energy particles born from the relentless spin of a stellar corpse. How do these distinct sources, the brief supernova and the enduring pulsar, weave together to create the single, unified rain we experience? This diffuse glow is the universe's own way of illuminating its hidden highways. While our eyes see a band of stars arching across the night sky, gamma-ray telescopes reveal a completely different Milky Way, one painted in broad, luminous strokes of high-energy light. This is not the sharp pinpoint of a pulsar or the brief flash of a distant explosion. It is a soft, all-encompassing radiance that fills the spaces between the stars, a permanent, high-energy twilight that tells us where the invisible sea of cosmic rays is most dense. The source of this light is a fundamental conversation between the cosmic ray rain and the galaxy itself. When a high-energy proton, traveling at nearly the speed of light, collides with a slow-moving proton from a cloud of interstellar hydrogen gas, the encounter is so violent it can create new matter. The collision forges short-lived particles called pions, which almost instantly decay into pure energy in the form of gamma-ray photons. Every point of this soft gamma-ray glow is therefore a signpost, marking the spot where an invisible cosmic ray has just met a fragment of galactic gas. This turns the entire galaxy into a natural particle detector, with every cloud of interstellar material acting as a luminous screen. By meticulously charting the intensity of this gamma-ray fog, scientists can work backwards. A brighter glow in a particular spiral arm indicates a higher density of cosmic rays slamming into the gas clouds there. A fainter region suggests a cosmic ray desert. Missions like the Fermi Gamma-Ray Space Telescope have spent years building this panoramic map, and the picture it reveals is breathtaking. We now have a chart of the cosmic ray weather patterns across the entire galaxy. We can see the vast, energetic bubbles blown by ancient supernova, their shockwaves still visible as bright gamma-ray rings where they churn the cosmic ray sea. We can trace the spiral arms not just by the stars they contain, but by the bright, diffuse gamma-ray rivers that flow along them, showing where the cosmic rays are funneled and concentrated by the galaxy's magnetic fields. This is how we see the ocean we are swimming in. Our solar system is not floating in a uniform bath. We are traveling through a dynamic, structured medium of high-energy particles, with currents and eddies and storms, all made visible by the faint gamma-ray light they spark from the interstellar mist. This grand, glowing map confirms that the cosmic network is not a mere abstraction. It is a physical, turbulent environment, and we are living deep inside it. The invisible rain falling upon us is also a silent, universal clock. The same high-energy particles that spark lightning and influence evolution also generate a radioactive form of carbon in our upper atmosphere. When a cosmic ray neutron, itself a secondary particle from an air shower, strikes a stable nitrogen atom, it transforms it. The atom becomes carbon-14, a radioactive isotope that behaves just like ordinary carbon but decays at a perfectly predictable rate over thousands of years. This newly forged carbon immediately bonds with oxygen to form carbon dioxide, which is then breathed in by every plant on the planet. Through the food web, this radioactive carbon is incorporated into the tissue of every animal, every blade of grass, every human being. For as long as an organism is alive, it maintains a steady level of carbon-14, consistently replenished from the atmosphere. But the moment life ends, that replenishment stops. The radioactive clock starts ticking, and the carbon-14 begins its slow, inexorable decay back into stable nitrogen. By measuring how much of this isotope remains in an ancient piece of wood, a fragment of bone, or a scrap of cloth, scientists can calculate precisely how long ago that organism last drew breath. This is radiocarbon dating, the revolutionary tool that allows us to read the chronology of our own history. The very timeline of human civilization, from the construction of Stonehenge to the final journey of Ötzi the Iceman, is written in this faint cosmic radioactivity. Our ability to peer into the deep past, to understand the rise and fall of ancient cultures, is fundamentally calibrated by the intensity of the cosmic ray flux from our galaxy. This means the clock that measures our history is not set on Earth. It is set by the sun and the stars. The production rate of carbon-14 is not a constant. It fluctuates with the strength of the solar wind, which modulates the cosmic rays reaching our atmosphere. During periods of high solar activity, fewer cosmic rays get through, and less carbon-14 is produced. During grand solar minima, the cosmic ray flux increases, and more of the radioactive carbon is generated. To account for these cosmic variations, scientists have painstakingly built calibration curves by dating ancient tree rings and ice cores of known age. These curves reveal the long-term heartbeat of our star, imprinted directly onto the archaeological record. When a researcher dates a Viking longship, they are not just reading a number from a sample. They are matching its radioactive signature against a calendar that has been shaped by the sun's activity over millennia. This intricate connection reveals that our planet's biography and the galaxy's weather are one and the same story. The deep time of Earth is intrinsically woven into the dynamic life of the cosmos, with every dated artifact serving as a testament to this eternal, invisible dialogue. The edge of our solar system is not marked by the orbit of a distant planet, but by an invisible, shifting frontier. It is the boundary of the heliosphere, the final reach of the sun's protective wind, and for decades it was a theoretical line on a chart. Then, in 2012 and 2018, humanity touched it. The Voyager 1 and Voyager 2 spacecraft, after journeys lasting more than 40 years, crossed the heliopause. They left the sun's domain and sailed into the interstellar ocean. Their most immediate and visceral discovery was a surge. The moment they pierced that cosmic shoreline, their instruments registered a dramatic jump in galactic cosmic rays. It was a direct confirmation of the heliosphere's role as a colossal shield. Inside the bubble, the Sun's magnetic influence holds back a significant portion of the galactic particle storm. Outside, that buffer vanishes, and the probes were suddenly immersed in the raw, unfiltered environment of the galaxy. This was not a model or an inference. It was a measurement, our first true taste of the unmodulated cosmic sea that fills the space between the stars. These veteran explorers are now true interstellar travelers, sampling cosmic rays that have journeyed across vast, dark reaches untouched by any star's wind. Their data streams back as whispers from the void, each one a priceless sample from a realm we have only just begun to explore. Our solar system is currently sailing through a galactic neighborhood, a region of space known as the local interstellar cloud. This is not a cloud in the earthly sense, but a tenuous bubble of slightly denser gas and dust about 30 light-years across, through which our Sun and its planets are moving. This local environment acts as the first filter, the initial frontier that all galactic cosmic rays must cross before they even encounter the Sun's protective heliosphere. The very nature of this cloud, its density and magnetic structure, gently sculpts the river of particles flowing into our solar backyard. It is the immediate galactic weather through which our entire system voyages. This means the cosmic rays that eventually reach you are not just messengers from distant cataclysms. They are also imprinted with the signature of our local interstellar space, a direct sample of the galactic medium just beyond our doorstep. The heliosphere itself is not a rigid shield. It is a dynamic interface, a magnetic bubble that pushes back against the pressure of this cloud. The balance between the outward push of the solar wind and the inward pressure of the interstellar cloud determines the exact size and shape of our protective bubble. When our solar system passes through a slightly denser knot of gas within the cloud, the heliosphere can compress, allowing a subtle increase in the number of lower-energy cosmic rays to slip through its defenses. Conversely, as we move into a more rarefied section, the bubble may expand, offering a slightly stronger buffer. This ongoing, gentle pressure dance directly modulates the intensity of the cosmic ray rain that drenches the inner solar system, providing a slow, rhythmic variation in the background radiation that has been a constant throughout Earth's long history. So the connection is even more intimate than a link to far-off stars. The properties of the cosmic rays threading through you at this very moment are shaped by the specific patch of galactic real estate our solar system is currently traversing. We are not just connected to the universe, we are immersed in its local climate, breathing the subtle currents of our immediate galactic surroundings. The hunt for another living world forces us to look beyond water and air. A planet could orbit within its star's so-called habitable zone and still be a cosmic wasteland, its surface scoured by an invisible storm. The true recipe for life requires a specific kind of shelter, and the intensity of the cosmic ray rain may be the deciding factor. Every star system in the galaxy creates its own protective bubble, an astrosphere shaped by the star's stellar wind. Our Sun provides a robust shield, its constant outward flow of particles pushing back against the galactic deluge, but not all stars are so generous. Consider a planet orbiting a common M-dwarf star. These stars are often magnetically turbulent, prone to violent flares that can blast away any nascent atmosphere. Worse, their stellar winds are typically feeble, creating only a shrunken, weak astrosphere. For a planet close enough to be warm, this means lying almost fully exposed to the galaxy's relentless particle radiation. The surface would be bathed in a downpour of cosmic rays hundreds or thousands of times more intense than what we experience on Earth. This constant, high-energy bombardment would not only deliver a harmful radiation dose to any potential life forms, it would also aggressively strip away the planet's atmosphere over cosmic time. evaporating the very air and oceans that life needs to begin. The presence of a strong global magnetic field, like Earth's, could offer some defense, but even that may not be enough against such a sustained, point-blank assault. This cosmic context transforms our search for life. We are no longer just looking for a warm, rocky planet. We are searching for a world with the right stellar guardian, a star capable of maintaining a sturdy magnetic umbrella against the galactic weather. The gentle rain that connects us to the stars here on Earth would, on another world, be a torrential flood capable of washing away the fragile beginnings of biology. This reveals a profound galactic filter. The universe may be filled with potentially habitable planets, but only those orbiting within a well-shielded stellar environment may ever have the chance to cultivate that fragile spark. The invisible rain has told its story, but the final chapters are still being written by the next generation of cosmic listeners. Our current maps of the high-energy sky, built from the echoes of air showers and the faint glow of gamma rays, are like the first charts of a new continent, full of promise but lacking in fine detail. The future of this entire field rests on a new class of observatories, designed with a singular purpose: to catch the universe's whispers with a clarity we have never before possessed. On the ground, the Cherenkov Telescope Array is rising, a global endeavor that will transform our view of the violent cosmos. Instead of a few large telescopes, it will consist of over 100 individual instruments spread across 2 continents, one in the Canary Islands for the northern sky and another in the Chilean Andes for the southern. This vast network will function as a single, colossal eye, capturing the faint, fleeting flashes of Cherenkov light from cosmic ray air showers with a resolution dozens of times sharper than any existing facility. It will see the gamma-ray sky in breathtaking detail, allowing us to match specific cosmic ray events to their source objects with a precision that was once a distant dream. We will no longer just see hotspots on a statistical map. We will watch individual supernova remnants and active galactic nuclei as they actively accelerate particles, witnessing the cosmic engines at work in real time. In space, new detectors are being designed to bypass the atmospheric filter altogether. Missions will orbit above our planet's protective blanket, directly sampling the primary cosmic rays before they shatter against the air. These instruments will measure the charge and mass of each incoming nucleus with exquisite accuracy, reading the isotopic clock embedded within them to determine not just their energy, but their age and the specific stellar forge that created them. This direct sampling from the vacuum of space is like moving from studying the ripples in a pond to collecting the raindrops themselves as they fall. The combined power of these ground and space-based observatories will open a new window on the universe's most extreme processes. They will hunt for the sources of the oh my god particles, probing energies so high they test the foundations of physics itself. They will sift through the endless rain of particles, searching for the subtle, telltale excess of antimatter or a specific energy signature that could finally reveal the identity of dark matter. Every unexplained spike in the data, every anomalous particle that does not fit the known models, is a potential doorway to a new law of nature or a new type of cosmic object. This is not merely an upgrade in technology, it is a fundamental shift in our perception. We are moving from listening to the cosmos's faint static to understanding its distinct language, from tracing broad connections to reading the specific, signed letters sent from across the galaxy. This cosmic connection rewrites our place in the universe. We are taught to see the cosmos as a vast collection of separate objects, distant stars and alien galaxies that exist in splendid isolation from our tiny world. Yet the silent, ceaseless rain of cosmic rays reveals a deeper truth. The universe is not a collection of things. It is a single, flowing event, a dynamic and deeply interconnected system. The very substance of your body is a crossroads. A particle that once resided in the heart of a star in another galaxy, forged in nuclear fires billions of years ago, can end its journey by striking a molecule in the air you breathe. That interaction may contribute to a cloud formation that shades a continent, or it may cause a subtle genetic shift in a living cell, a tiny nudge in the grand, slow dance of evolution. This is not a metaphor, it is a physical, material link written into the laws of physics. You are not a passive observer looking out at a separate universe. You are a region of the cosmos that has temporarily become complex enough to feel the connections that have always been there. This challenges our most basic sense of isolation. We build borders and think in terms of us and them, here and there. But the universe operates on a principle of fundamental unity. The same forces that sculpt galaxies are at work in the spin of an electron around an atom. The same particles that thread through the emptiness between stars are threading through you at this very moment. You are not in the universe is in you. This realization is both humbling and empowering. It dissolves the illusion of separation and highlights our integral role within the cosmic whole. We are not insignificant specks in a cold, indifferent void. We are the universe becoming conscious of itself, a way for the cosmos to understand its own beautiful and violent nature. The journey of a single cosmic ray from a stellar cataclysm to the air above your head is a thread in that unfolding story of self-discovery. This silent rain is the bloodstream of the galaxy itself, from the furious death of a star to the gentle mutation in a strand of DNA. Every thread we have followed converges into a single, undeniable truth. Cosmic rays are the fundamental circulatory system for the cosmos, a relentless flow that distributes not just matter, but energy and information across the incomprehensible voids. They carry the raw ingredients of stars from their stellar forges, seeding the galaxy with the very elements that make planets and life possible. They transport the immense power of supermassive black holes and colliding neutron stars, delivering that energy directly into the atmosphere of a waiting world. This is not a collection of separate phenomena. It is one coherent, galaxy-spanning narrative. The life cycle of a star is linked directly to the evolution of a galaxy, which is linked to the climate of a planet, which is linked to the story of life upon it. Every time you feel a breeze, you are feeling air that has been ionized by a particle from a distant cataclysm. Every time you look at a lightning flash, you are seeing the final step in a chain reaction that began millions of years ago. This cosmic web means that the universe operates as a single, integrated entity. The death of one star becomes the breath of another world, and the spin of a stellar corpse becomes a subtle timer for biological change. You are not just connected to this web, you are a living, breathing part of its endless, flowing story. This single, epic journey of a particle reveals a cosmos woven together by invisible threads. We have followed these messengers from supernova blasts to the upper atmosphere, from the hearts of distant galaxies to the very DNA within us. They are far more than a scientific curiosity. They are the fundamental proof that the universe is a single, breathing entity. These particles remind us that we are not mere observers on a lonely rock, gazing out at a separate cosmos. We are active participants in its grand, unfolding story. The next time you stand beneath the night sky, remember the silent, constant rain. You are being gently probed by fragments of distant stars and galaxies, a physical reminder that the boundary between you and the cosmos is an illusion. We are all part of something truly vast and wondrous. If this interconnected view of the universe has captivated you, consider joining our community for more journeys into the deepest mysteries of space.